All right, so let's look at example 2 from the textbook. Oops, get that green. Example 2. And so we have a parameterization where x is equal to t squared, y is equal to t plus 1, and we're going to be doing this, though, with an open interval from negative infinity to positive infinity. So I'm going to look at some values for t. I'm going to see what they create for values of x and y, and then we'll graph it. A good place to start whenever graphing is 0, and since we can go towards positive and negative infinity, we'll just go an equal amount on either side of that to see if anything interesting happens. And so x is t squared, so 9, 4, and 1, 0, 1, 4, and 9, and y is t plus 1. So negative 2, negative 1, 0, 1, 2, 3, 4. So we'll want to graph this. Let's give myself an axis here. And let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're negative 2, I think. 1, negative 2, 1, 2, 3, 4. So let's plot these points on here nicely for ourselves then. So 9, negative 2. So there's 9 for x. There's negative 2. 4, negative 1. 1, 2, 3, 4. Negative 1. 1 and 0. 0 and 1. 1 and 2. 4 and 3. And 9 and positive 4. And so we have a parabola that's turned on its side. We have a vertex here and an axis of symmetry at y equals 1. Notice the direction of motion. As the parameter t increases, we move inwards towards the vertex, and as the parameter t increases, we move outwards from the vertex. And so this parameter is a really good way of looking at a parabola that is in x and not y, right? Because what is this? This is x equals y minus 1 squared. Let's see, does that work out right? If y is 0, x is 1. If y is 1, x is 0. If y is 2, x is 1. I think this works for all of these. This would be the relationship in non-parameterized form. Let me just double check here. Y is 4. 4 minus 1 is 3. Yep. Y is negative 2. Negative 3. Yep. And so this is our parameterized form of it. All right, let's look at one that we've probably seen a lot. It was the basis of how we worked our way through trig. And in a way, the unit circle was a parameterization of a circle equation where we used angle theta as our parameter. And so we were able to create our ways of moving around the xy plane for an equation of a circle. So let's develop the unit circle using the equation of a circle, and then we'll show what this looks like parameterized. So the equation of a circle was x minus h squared plus y minus k squared equal to r squared, where h comma k is the center and r is the radius. So let's make a unit circle somewhere. And so by making this unit circle, we've made our center 0, 0, and our parameter, we're going to make t, and the increase in direction of t, we're going to move in a counterclockwise fashion. So t increases counterclockwise. Then what we're going to do is just to make a unit circle, then in only one way around, we can look at, well, let's see here. If I make the circle x squared plus y squared equals 1, because that's what happens with our unit circle. We have a length of 1 here. Then in our right angle trigonometry said whatever our x value was equivalent to the cosine of the angle. And whatever the y value was the sine of the angle. And so we've been living with a parameterization where the parameter of the angle gave us a geometric shape, and our trig identities let us parameterize. So we were able to graph these out. I'm not going to go through and repeat all of the identities on the unit circle, but this is an example of parameterization you have been doing in your previous studies that have led you up to here. A nice little twist could be added, that if we add a cosine t, y a sine t, then we've added a as being the radius. And we're able to increase the radius as some parameter a and find the points as these two parameterized function. And so centered on the origin, we can parameterize that equation. Let's look at a parameterization. We'll make a sketch of a function or of a relationship, and we'll use the parameterization to explore it. So we're going to look at x equals t plus 1 over t, and y equals t minus 1 over t. And we're going to do this for all t's greater than 0. So we'll make a table of values. I don't know, I think because 1 over t is in both of these, I think a t and a 1 over t are needed to do our graphing. And since t starts at 0, we're going to work our way up. I have an inverse here, so how do we look at this? If I were to plop in a 1, I'd get a tenth. If I'd plop in a tenth, I'd get a 10. So what I want to do is I kind of want to respect this kind of logarithmically. So 1/10 gives me a 10 here. 5/10 gives me a 2 here. 1 gives me a 1. 2 gives me a half. 5 gives me a fifth. And a 10 gives me a tenth. Alright, kinda just getting some numbers around that I can get an idea of how to plot this. And so X and Y, really looking for an offset, right? At 0, I'm at 0 and 0. I think t is greater than, so this doesn't really exist here. So we can't get to 0, I guess, would be a thing here. And let's see, at 1/10, then an x plus this is 10.1, and y is 9.9 negatively. Let's see, yeah, because that would be subtraction. This is the subtractive part. At 5/10, then in, let's see, 5/10 or 2. For this, we're going to have 2 plus 5/10 or 2 plus a half, so 2.5. And then on the other side, this is going to be 0.5 minus 2, so negative 1.5. 1 minus 1, this is going to be 0. Let's see. Or not 0, it's going to be 1 plus 1. Whoops. Yeah, so 1 plus 1 is 2, and 1 minus 1 is 0. And then in here, we're going to have 2 plus a half. So this is 2.5. And then now we're going to have 2 minus 2. Let's see, 2.5. 2, 1 half, 2, so 2.5. And 2 minus a half is 1.5. Looks like there's some symmetry going on here. 5 plus a fifth is 5.2, and 5 minus a fifth is 4.8, and 10 plus a tenth is 10.1, and 10 minus a tenth is 9.9. Definitely seeing some symmetry in these x and y values here. I didn't complete the symmetry in how I looked at it, but I think going up logarithmically gave me an idea of what was going on. And I think if I sketch this a little bit, it's funny that I can look at this as a line where t minus 1 half kind of has a line-like selection to it. Something is happening or happening near a line here. But let's look at some values that we get here. So when x is 2, y is 0. So I'll come over 1, 2. There's x is 2. Let's go 2.5. Then y is negative 1.5 and positive 1.5. And if I go out to 10.1, way out here, then we have negative 9.9 and positive 9.9. If we sketch this, this isn't really parabolic. It doesn't have the same symmetry as a parabola. And let's see, if I look at my parameters of t, as t is getting bigger, I come in from down here, and we can't be at 0 because we can't do the 1 over t at 0. And if you've studied a little bit in your pre-calc or you've seen this before, this really looks like our hyperbola, or at least one side of a hyperbola. And we'll talk about conic sections further on in this chapter. And so these are two examples of parameterizations for shapes that are failing the vertical line test. So functional calculus has let us down, but we've now been able to create two functions to talk about these shapes, and we're able to take those two functions and define any point in the xy plane, and notice that these functions lock in a curve. We're going to look at some cycloids and some kind of famous parameterized curves in the next video that solve some actually very important problems that in the basis of mechanics and dynamics, things like Tautochrones and Brachiostones, like what gets a beat across the wire in the quickest time, which underlay an entire concept of mechanics, the Lagrangian mechanics, which is based off the principle of least action. But we don't need to worry about the principle of least action, but we do need to develop the mathematical skills to deal with it.